So I'm going to try and do justice to this forum, and it's an honor to be told that as scientists we're also artists. So let's see if I can keep your attention and show you if there is some creativity involved in what we do. I wasn't sure about the audience that would be here today in terms of the background and so forth, and what would be the impetus, because the title is a bit, I guess, the word is in search of cheap and clean energy. Cheap is the operative word. We're not there yet. I'm sort of giving away the punchline. We don't have access to cheap and clean energy. We have access to cheap energy and we have access to clean energy, but merging those two is the hard part, and that is the issue that we have. So just to get everybody together on the same baseline, I'm going to talk about what exactly is energy. First of all, I want to be clear. Energy basically is a type of entity, a currency that we use quite a bit, and it's used for a variety of purposes. From the point of view of transportation, you put gasoline in your car, and that provides energy to the car to move it forward. So energy is stored in gasoline, the petrol that you're using. So that is an energy storage material, or it's a fuel. It's an energy fuel, gasoline. When it comes to our house, everything you see around you is running on electricity. So electricity or electrical energy is another type of energy. Currently, we do not have a rampant availability of electric cars, but you can have electric cars that also run on electricity. Currently, our cars do not run on electricity. They run on gasoline, and that's an internal combustion engine, and there's a physics behind it. So this is, and as you probably have realized, this sort of runs our world. Just think about it for a moment that you don't have access to electricity. How completely shut off your life would be in terms of your ability to work day to day. Not only that, the ability to feed yourself, because you have to realize now the entire farming community, the farming is based on energy aspect, because you have to irrigate your farms, you have to supply the food that is farmed or grown in one place, and it has to be transported to another place. And without access to energy, all of those infrastructures and those processes would be hampered incredibly. So as a society, it is one of our most important currencies we have, in terms of that we sort of use day to day, and hence the cost of it is very important. So I'm going to sort of take a little step back and explain to you what the problem is, or what is this problem that we have with respect to using this energy. So let's start off with the population, and all of this data is available on internet, so if anybody wants it. So these are all projections. As you can see, the world population is increasing. Currently we are about 7.2, 7.3 billion people in the world, and the number of people is only going to increase. There is no sign, as you can see in terms of the best computer models and so forth, that are showing any signs that we are tapering off in our population worldwide. Okay? And why is this important? Because remember, the more human beings we have on the planet, the more energy we will be consuming. But let's be a little specific about India. So this is recent data. I tried to get as recent a piece of data as I could. And you will see the population of our country with respect to three other countries. And as you can see, I do not know if you can tell, but China seems to be tapering off just a little bit. It seems to be plateauing out. But the rise of the Indian population is still quite vertical. And as you perhaps read and perhaps also realize that, there is a chance that we will surpass China in the foreseeable future, perhaps in the next decade. I do not know how quickly, but there is a chance that India will surpass China and become the most populous country in the world, which is great. There's something to be said for being the world's first in some, many things we are, I think, but in population, definitely we will be surpassing them, right? So in terms of all the countries on the planet, India, having one of the largest populations, really needs to consider energy aspects very, very seriously, much more so than many of the other countries. Okay? Now I'm going to show you another piece of data, which is how much energy do you think we consume? So we have the second largest population currently in the world. Now, if I were to sort of look at the electricity supply throughout all the countries, do you think we are the second largest consumer of electricity because we are the second largest populous country in the world? And the fact is no, that, you know, and this sort of graph kind of gives you that sort of impression. So what I'm trying to show you here is something called the Human Development Index. It's on the y-axis, okay? It's basically the quality of life, the prosperity, education, lifespan. A lot of these parameters go in towards calculating your data point on the y-axis, okay? So the higher up you are on the y-axis means the more affluent is your society, the better is your society, okay? Now on the x-axis, which is the bottom line there, it's actually the annual electricity use per capita, per person. So it's sort of normalized to per person. So what this graph is trying to show you is, if you look at the names on the top right side of the graph, you'll see that the richer the country is, the more it's using electricity, all right? The more demand for energy per person there is, right? And that is why India, despite India being a very populous country, our energy use is actually not very high, okay? So you'll say, well, that's a very good thing in some respects. But you have to keep in mind the reason India's use of electricity is less is because in India we have very a large strata of society. We have the very, very poor to the very, very rich. The very, very rich would be over there, okay? The elite of Bombay and Delhi and Bangalore. If you calculate their per capita use because of the number of cars they have, the number of TVs they have in their house, how big their house is, how many ACs they have, the per capita use of those rich people would be, the affluent people would be over there. But because we have a large poor population, all right, many of them don't even have electricity, so it normalizes out to a very small number. So I hope you're sort of, yes?
You have something written sustainable and ethical. Right?
Yes, so sustainable and ethical is the area that people think if you're in that region, you will have a good prosperity in your quality of life in your country, but if you can maintain your per capita use in that region, you are not going to be producing a lot of pollution, and I will come back to that, okay? It's not to say that the countries US and Canada are producing a lot of pollution, please. The fact is that they're using a lot of electricity. That is all it's saying, per person, right? And it's saying that India is using not as much. And if we are in that sort of curvous region, it has been projected that that is sort of the ethical area in terms of what should be considered normal, all right?
Why is US, China, and India in red?
In red. To highlight these three countries currently, because it's the one that everyone talks about. US is one of the most affluent, richest societies in the world, all right? This is not GDP here, all right? But not the GDP of a country, but in terms of per capita wealth. US is one of the richer countries, along with Norway and Sweden. China and India are the more populous countries, and there's another reason we've highlighted, or I've highlighted China and India here, and that is because of the growth rate of the countries. Right? So there are lots of parameters I'm throwing at you, and India falls at various stages in those parameters. So this is the GDP forecast. Now GDP keeps changing depending on a variety of parameters, so there's only so much accurate data you can get. So you can see India and China over the years, 2017 is in light blue, 2018 is in the dark blue. They're sort of fighting with each other as to who has the highest GDP. What does GDP really refer to, if you think about it? Is the growth of the country. GDP, this is the GDP, not the growth, but in terms of the actual GDP. This is the actual GDP, and this was a June 2017 forecast. The red line is the forecast of June 2017. I don't know what the number for June 2017 ended up being, but as you can see, the fact is, we as a country, along with China, are getting richer, basically. Think about it like that, compared to some of the other countries. USA does not have that level of GDP right now. Okay, we are growing in terms of wealth per person as a country. We are growing in terms of the number of people in our country. So the wealthier we're becoming means we're going further up in that previous curve that I showed you.
GDP is just gross domestic product. It's the overall.
This is the increase, growth.
this has to be the growth in terms of over,
Okay.
as it's in terms of 6% growth, 5% growth, 7%. And you know, in one hand, you always want to hear these things in the newspaper, which is, oh, we should have 8% growth, or you know, the federal bank is saying 7% growth, and everybody gets happy that you know we are surpassing our projected expectations. Means that we are getting richer. So on one hand, people become happy, but there are side effects to this. The side effect is when you are becoming richer, when you have more money in your wallet, what are you doing with that money? You're inevitably buying consumer products that utilize electricity or energy. You're inevitably buying a second car or a second scooter, something, you understand, more transportation, or you're having access to better transportation that uses more energy. You're perhaps buying an AC, you're buying another TV, you're buying a better mobile phone that perhaps might use more electricity, all right? So there's a cost that comes with becoming wealthier. So I hope I'm sort of laying down the foundation of what the issue is. So now where is this electricity in our country currently coming from, all right? I'm not talking about petrol right now, just the electricity, because there are other forms of energy as I highlighted. I'm just talking about electrical energy currently, electricity. So this is the current data for 2017, 2018. This is your big pie chart. And what you see in black is coal. All right, 75% of our electrical needs, electrical energy needs is being supplied by coal in this country at this day and age. And how do we use it? We have what are called coal thermal plants or coal power plants. They look like that, okay? There are many, many, many in our country, and they're being commissioned. New ones are being commissioned. There was a new one commissioned around 2014, 2015, all right? Coal plants were being commissioned, means the government realized, look, our GDP is increasing, people are getting wealthier, we cannot have power outages, we need to supply electricity, everybody wants 24-hour supply. We have to fulfill this need, therefore build more coal power plants, okay? So that's why it's in black. And then we'll come to all the other colors, all right? Now keep in mind, why are we relying on coal predominantly? Coal, India has access inherently to coal. We have about, on the planet, I don't know about Indian supply, but on planet, there's projected coal supply over hundreds of years, all right? Oil supply is always said to be only another 20 years or 30 years, and it keeps changing. You know, in the 70s, they said, oh, another 20 years. 90s came and went, and we still have oil, all right? So I do not know how much oil there is still underground in Saudi Arabia, but we have oil for another 10, 20 years, according to all the oil companies. But coal is there for at least a minimum of another 150 to 200 years. So we have a lot of coal still available to us, all right? And that is what we're using to supply our need. Now, okay? So it's sort of, you know, just realize that, and you know what the options are, and I'll come to it. And this is in terms of oil, which is the transportation form of energy if you want to use petrol. So this is the projected oil consumption for our country with respect to US and China. And you will see over a period of 2010 to 2030, the projected oil consumption is higher. Now you understand why the projected oil consumption is higher? Because our population is not slowing down. China's population is slowing down, and our GDP is also. So you see, not only is our population increasing, but our quality of life is increasing, and therefore our energy needs are needed. And we will be the heaviest consumer, or the heaviest, fastest growth of energy requirement on the whole planet as a country in terms of percentage increase of the energy requirement. You understand? And you cannot stop that, because you cannot tell people don't buy a second car, don't buy another TV, don't buy an AC, because if they're making more money, they will do that. And there's nothing wrong with that, because they'll say, well, others have it, so why can't I have it? So you cannot stop this need. You know, that's a human nature. So we have to try and circumvent the problem at a further down in terms of the energy supply chain. So all of that is fine and dandy, but now you know what happens when you use lots of coal and you use lots of oil, all right? These are called non-renewable sources of energy, because there is not an infinite supply, but there is a finite supply of this energy present. And this is the pollution, and I'll just show you kind of images. This is what Beijing did. China can do this, you do seeding method and you can clean up your atmosphere. It costs a lot of money, it costs a lot of energy to clean up the atmosphere, but that is what a nice clean day looks like in Beijing. And I was trying to find a similar picture for Delhi, with but I couldn't find one. I only saw the polluted images of Delhi and Bombay, and I don't think there's a major city in India that you do not see this sort of a haze. This is smog. This is carbon particles in the air that you're breathing. This has health effects. This has, the cost of us using all these forms of energy, or coal, basically burning coal and burning gasoline, has a huge cost that we might think that we are not paying, but you are paying in terms of health issues, in terms of the buildings spoiling. You will see a lot of fungus growth, and because the pH of the air changes, and there are lots of side effects of having contaminated air to breathe, contaminated water to have. So what about the renewable sources of energy? So in that respect, I'll just very briefly talk about the ones that everyone's familiar with. Hydroelectric is a very interesting one. So this is a hydroelectric dam. This is in Hyderabad or somewhere in Andhra. You know how it works. Basically what you do is you have a large amount of water piled up. It has a high amount of potential energy, as it were, and you drop it from a huge height. When you drop it from a huge height, it turns some turbine engines, which in turn activates a generator that generates electricity. All right. So it's just basically dropping water from a huge height is what a hydroelectric power is. All right. And we can go back to that pie chart. Hydroelectric was written in there, and that was one of the larger areas. But as you can see, you need a large amount of space. You need to create these dams, means you're creating these false lakes. You have to empty out villages. This is infrastructure-wise, in terms of space-wise, you need a large amount of space, and it's not that you're generating that many gigawatts of energy immediately. All right. Coal is a lot. In terms of energy per area, in terms of making a coal power plant, and how much energy, what is the size of the power plant, how much energy you can get from it, is far more feasible than compared to many of these renewable sources. And so that's another issue. All right. So another one is wind farms and wind generation. All right. So again, this is just wind turning the turbines and then generating electricity that way. So here you see a wind farm. It's in Tamil Nadu. You're restricted to obviously areas where you have a large amount of wind, and constantly you want a large amount of wind. And keep in mind with all of these things, the hydroelectric power, the wind farms, you might be generating electricity, but you're not storing it. Means that only when the wind is blowing, you're generating it. And if you're not able to use it at that time, if it's not attached to a grid, if no one has switched on a light bulb, that energy will go to waste. So in addition to this, you need a large space for battery storage. All right. So keep that at the back of your mind, which very few people discuss, but energy storage has to be coupled with energy acquisition. And then the other one that everyone's very familiar with is the photovoltaic cells, and these are silicon solar cells. There are lots of different kinds of solar cells. These are silicon ones that you see in the background. These are in Gujarat. When Modi was the chief minister there, he created quite a few of these solar cell farms. They're fantastic, but you need a large amount of space, and we can discuss all the issues with the photovoltaics as well. But as you saw in that pie chart, our infrastructure in India devoted to photovoltaics or wind farms or hydroelectric is very, very small. All right. Now, so that is sort of the background of what I hope most of you are familiar with. Now I'm going to talk about something slightly different. I'm going to go a little bit into it deeper because it's something that we tend to work on in our lab. So there's another type of molecule that I want to discuss today. Some of you might be familiar, some of you may not, but I'll just sort of talk about it. It's called hydrogen gas. Hydrogen gas is a very simple molecule. It's just two atoms. Both of them have only a single. When you see the periodic table, those of you familiar with, it's the smallest atom there in the corner, and it's just got one electron in it. There are various representations of it. Now, why do I want to talk about hydrogen gas? Because it's a molecule Just like gasoline, when you combust gasoline, it releases energy. This also releases energy when you combust it. Let's look at the numbers a little bit. All right. So this table is sort of showing you how these are all chemicals on the left side of that table. Okay. You'll see words that I hope all of you are familiar with. And on the extreme right, you will see the amount of energy. Don't worry about the units, just look at the numbers. All right. So you'll see how basically batteries have very small energy associated with it. That is why we do not run our entire house on a battery. All right. Whereas you'll see why we use wood for cooking. TNT is an explosive. You know how much energy gets released in TNT. Diesel and gasoline are what we're using currently in our cars. All those values are normalized to per kilogram. If you just see the units up there, mg just means megajoules. Kgs, therefore, it's normalized per weight. Now I want to show you how much energy hydrogen gas has per weight. All right. As you can see, it's a huge amount of energy in that bond. All I have to do is break that bond and this energy gets released. All right. So energy density means amount of energy per kilogram is very large. So right now, if you fill up your car with petrol, you have, I don't know, a 30-40 liter engine. So just imagine if you were filling it instead of with gasoline as a fuel, as opposed to that you use hydrogen as a fuel, you're going to be using a fraction of that amount. It's a gas, agreed, it's not a liquid at room temperature, and there are ways we can work around that aspect, but you're using a very small amount of that gas, and the best part is you're releasing a lot of energy. The other thing is, with combustion, you know, when you combust it, the energy gets released very fast. And that is the best part, means your car will go like a Formula 1 car if you can do it properly in terms of if you have the right fuel cell, okay? So it's a very potent form of energy. In fact, it's what is used in rockets. All the space satellites and everything use hydrogen gas as their fuel, right? And now, why is this interesting? It has no carbon atom in the structure, all right? The diesel fuel, jet fuel, gasoline, ethanol, coal, methanol, wood, TNT, all those names in blue, they all have carbon in it. When you have carbon in the molecular formula, it forms CO2 when you burn it, all right? I don't want to bore you with too much chemistry or equations, so I'm trying to keep it very simple. So the top equation is basically methane. CH4 is a gas, it's methane, it's a carbon-based, and you burn it in oxygen. So that is what combustion is, okay? And what I'm trying to show you on the right side is you see CO2, and that is the bad thing. You're releasing energy. When you burn methane, you're releasing energy, fantastic, but you're getting that CO2. And the same equation I'm showing you with hydrogen, and you'll see there's no CO2, water is the byproduct. So not only we have a molecule that stores stores a lot of energy in it, excuse the language, but but it basically releases water, right? So there's no carbon dioxide, there's no pollution associated with it. And this is not something that is brand new. So here you see a transportation bus, and you see what's written on it: zero emission hydrogen fuel cell bus. So basically hydrogen is stored. Hydrogen is the fuel that is used in running this bus, and therefore the only byproduct or only emission from it is water, right? So you can use this bus, and people are using in their cities in the world that have public transportation based on this. And you'll say, well, why hasn't India done that? So India is doing that slowly. This is as of March 2018. This came out in India today. So as you can see from the title, India's first ever hydrogen fuel cell powered bus by Tata Motors is here. All right, made in India, bus emits only water. For public transportation, people are trying to use this as opposed to regular cars, because you need something called a fuel cell. You will have to replace what is called the internal combustion engine, which a normal car has, with something called a fuel cell. This fuel cell needs platinum in it. Platinum is an expensive metal. It won't be cheap. You can perhaps make a fuel cell car, but you just need to add an extra zero to the price, right? So this is where they're trying to market it more for cities, for buses, all right, for public transportation. Anywhere it helps to me, whether, you know, one answer doesn't solve all the problems. We have lots of different kinds of energy needs. So this is just, I'm just trying to explain why this one is being marketed. So this is great, you know, in principle this is happening. Tata is doing this. They're making these in Bangalore. I don't know which cities and you know how far it'll go, but that is the idea. So you'll say, great, what's the problem? Is there a problem? Well, the problem is, yes, we know we can burn hydrogen, right? Problem is, where do we get this hydrogen gas from, right? When the bus goes to a fueling station, it needs to fill itself up with hydrogen gas, not gasoline. Now, how do we get hydrogen gas? On this planet, there are no deposits of hydrogen gas. It's not like there's a pool of this gas, like a large Saudi Arabian reservoir somewhere lying in wherever that we can pump hydrogen gas. We need to make hydrogen gas. We do make hydrogen gas, as you know, we have access to it, but currently we make it through this route, right? We make it, it's an incomplete combustion of an organic material. And as you can see, you get 10 H2s on the right side, and this is burning again the same methane I showed you, but it's called a partial oxidation, all right? So what's the point of doing this if, you know, you are still releasing pollution here, all right?
Is that monoxide?
Yes, that's carbon monoxide. So it's partial oxidation, right?
Almost like poison.
It is a poison, not almost like a poison. But mind you, your car releases carbon monoxide. I do not, I mean, in movies, I do not know if you've seen, you know, you tie up the hose and you put it inside the car and you can kill people, or people kill themselves with, sorry, I'm digressing, but we release carbon monoxide. All the pollutants that you see in this air, this thing, you know, people having asthma and all of those issues, nitrous oxide, carbon monoxide, various sulfur compounds, that's all burning gasoline, and coal gives you all of those. So there's lots of carbon monoxide in our air outside there. So, but anyway, the point is, this is how we make hydrogen. So it's pointless to make hydrogen like this if you're not going to be, you know, you destroy the environment before you even start solving the problem, right? So how can we solve the problem? So this is where I hope a little bit of interest will happen. So the top reaction is what I've shown you already. Hydrogen is combusting to make water, and that releases energy, all right? If there are any of you who are chemists or have studied some chemistry, you'll know that every reaction is reversible, all right? So we can actually do the reverse reaction. We can take water, all right, and break it up and make hydrogen gas and water, oxygen, all right? So you might say, well, wait a minute, that doesn't make sense. It doesn't, the thing is this part. If one releases energy, the other one needs energy, all right? Because hydrogen molecule is the one that stores energy, you understand? So when you're doing this reaction, you have to dump energy into it, and what you're doing is, it's called water splitting. You're taking a water molecule, H2 is a water molecule, and you're splitting it, and you're making hydrogen gas and oxygen gas. Now you'll say, well, how do I split a water molecule? Water is all around us. We are not spontaneously, because this is what is, if it needs energy, means it's like climbing a mountain. Going down a mountain is easy. That is why, and we are going to do that, by the way, sorry. We're going to burn some hydrogen. You're going to see how much energy is stored in the hydrogen molecule. Going down the mountain is easy because you're releasing energy, right? Going up the mountain is the hard part, and that is what is there at the bottom. The question is, how do we do the bottom reaction without causing pollution in the process? Remember, the whole aim of all of this is, we want a zero pollution cycle, and we want a complete cycle. We want to make hydrogen from water, and we want to combust hydrogen to make water, right? It's not perfect. We will lose energy along the way, but it's still better than nothing because there won't be any pollution released. Now, splitting water is not actually difficult. There's something called electrolysis, and we'll also do that experiment. You might have heard of it. The word perhaps you've heard, electrolysis. It's basically what you do is you take remember, this reaction needs energy. The water molecule needs to be broken up, not heated. I can't heat the water molecule, all right? By heating it to high temperatures, it won't break it up. And even to heat it, I'll need electricity to heat it. So where is that energy going to come? Electrolysis is you take a reaction where you have two electrodes, and you try and do what is called an oxidation reduction reaction. I'm sorry, I'm going a little, for the non-chemist, this is water splitting has two things embedded in it. There's an oxidation reaction and there's a reduction reaction. And so that is what this does. On one side it releases hydrogen, the other side it releases oxygen. All right? But you need to attach, you see that V there, that's a battery. Now that battery or electricity, I need to use electricity to split that water molecule. The problem is currently the amount of electricity that I'm going to use, and I'm going to show you right here how to do that. Right now the amount of electricity that goes in doesn't make my energy cycle positive. I put in more energy and I only get a small amount of hydrogen out that I can use. Yes, it's a clean way, but the problem is I'm using more energy than I'm getting back in the process. So people don't like that. This has been around for 100 years. People have known about this. But people say that's not the best way to make it because you're spending more energy making it. So how do we circumvent this problem? All right? And I'll come back to that. So there are ways of circumventing this problem by changing the nature of the electrode, because this is catalysis. This is called electrocatalysis. So we can discuss this if you want, but the nature of the electrode, if you play with the chemistry of the electrodes, you can decrease the burden on the battery. All right, so you can decrease the amount of energy you need, and in principle you can do this cost effectively, but it means making very expensive electrode materials. Comes back to things like platinum. All right, platinum works really well, but it's expensive. So that is where the cost goes up. You understand? I said we can get clean energy, but it's not cheap.
So this part, didn't understand.
Okay, so I'll just, you see, I've got those two black and red things. Those are the two electrodes. It's called a cathode and anode. Those two, these electrodes, right now I'll show you with graphite. All right, these have to be metallic in nature. They have certain properties, and they actually decide the potential or how much burden I will need on the battery to drive this reaction. Okay?
They decide how much energy you'll need to drive the reaction.
I'll tell you why, because you see this cartoon, the way it's shown, it's highlighting a lot of things, because it's kind of like a molecule has to go and sit on the electrode, grab an electron from the electrode and say, oh, now I can break myself up in half, kind of thing. All right? It's kind of the material has to be conducive for the reaction to take place. If the material and this molecule don't like each other, there's no reason for what we call an electron transfer to take place. Remember, it's a reduction and an oxidation to take place. So electrons are going in and out. It's like little bits of the atoms have to go in and out. So it's kind of like if I want to take her scarf. You know, I have to come very close to her and be able to unwind the scarf from her and take it from her. Now, if she doesn't like me or she repels me, I'll never be close enough to take her scarf from her. So it's kind of like my electrode material has to be conducive to the molecule that I want to interact with and break up and do some reaction with. Is that
So if we use platinum instead of whatever else, graphite or whatever.
yes,
you're using,
life
it
is
will be
good.
more conducive.
Yes, life is very good, but then life is very expensive. And
That
we
will
go
be-
to Africa to get the
That will be
platinum.
a one-time expense only, no?
It'll be, okay, fantastic question. Huh?
Who will fund it? That amount of platinum.
Catalysis means yes, you do not have to replenish it, but reality is not good because there's leaching, there's degradation. No, just like a battery, you have a rechargeable battery in your phone. All right, I'm digressing again. If you are very good with your battery and you charge it only between 90 and 10, you understand, you don't overcharge it and let it go to 0, then you can maintain a good battery for a long time. But if you abuse it and you're constantly overcharging it all night for hours and hours unnecessarily, your battery dies off, right? Materials, everything in life has a shelf life. It doesn't retain itself. So even platinum does degrade over time. Okay, not as fast, but yes. It's not a one-time use, but it's not a, how should I say, maybe every X number of thousands of trials you'll need to change it.
So again, I'm not a chemist.
So, yeah.
Based on some articles that I would have read over the period of time, I'm trying to correlate to this. I remember there is a universal rule which says the total amount of energy and mass together in the universe remains constant.
Yes, correct.
If we are talking from that perspective, we use energy to create mass and then again create energy from there.
Right.
In the equation, how would you generate more energy than the energy that you consume if the mass remains constant?
We are not, no,
Is this a
here
process
I am
or-
still putting in more energy than, here I'm still using more energy than I will get back. Let me make,
Understood.
it
So
will-
how does platinum change that?
platinum decreases. Let's say if I was needing, I'll show you with a 9-volt battery, platinum will bring it down to, let's say, 3 volts. Okay? In principle, when I burn hydrogen, I only get back 1.23 volts.
And yet generate.
I will generate enough hydrogen for 1.23. I'll get 1.23 volts of energy back from the hydrogen I'm generating. All right? But 9 volt is still too high, whereas 3 or 2 or 1, 3 or 2 volts is still livable with.
Just to add to your question, if you are not,
Because I'm getting that, let's say, from solar cells or something like that.
if you are not doing it, say in any process, would I be correct to understand that when you're creating energy, there is always a loss of energy?
Absolutely, absolutely, guaranteed.
And you're trying to minimize that loss of energy. That
Exactly, exactly. That I will, whenever I'm creating anything to make an energy device, molecule, anything, I have to always put in more. Always. That's thermodynamics. The question is, how little can I put in more?
So it's a question of efficiency.
Efficiency of this reactor. The word efficiency is used quite a bit in various contexts, but in this case, is how much energy you've put in and how much energy you're getting back out. All right?
So waste, like you're minimizing waste.
Minimizing the waste, absolutely.
Excuse me.
Yeah.
I have tried it with stainless steel plates,
Right.
and we have tried it out in engineering college, and we used 21 plates, and the electric consumption was 10 amperes at 12 volts.
At 12 volts.
10 amperes with 12 volts. That means 1.2 kW.
1.2, sorry?
120. 120
Sorry,
volts.
0.12 kW. 10 ampere into 12
Right,
volts.
yes, yes,
0.12.
yes.
And we got a efficiency of 17% on that, and it was working wonderfully well. We saved 14 liters of diesel compared to, and you see, I did all this experiment in VJTI as well as in Pune,
Right.
and I have been very successful in that. Stainless steel, which costs practically nothing compared to platinum and all that. I have got the results with me.
Fantastic, but you have an efficiency of 17%. Platinum gives you an efficiency of 97%.
Maybe
That's
but
all.
it is too costly.
Exactly.
Correct.
So there are lots. So that's what I'm.
Yeah.
There are lots of ways around it.
Let us
Absolutely.
continue and then we can come
So
back.
that's why I didn't want to talk about it since the
Sure, of course.
discussion
We'll come
started.
back to it, yeah.
No, I think that is
Doing
exactly
better.
what most people are trying to do. In the efficiency of even 17. Let me give you a slightly different way. I'll come around out of this and talk about solar cells for a minute. Solar cells an efficiency of 20% only. Means the amount of energy that goes in, they only give you back 20%. But that energy is coming from sunlight. So it doesn't matter we're wasting 80%. So that is where I want to take this talk now. So this talk is using electricity to drive this reaction. All right. So yes, we still need to supply electricity, and hence this is called electrocatalysis. So there's still a burden on our system, on our grid system. All right. And we minimize that burden by changing the electrode. So we can improve efficiency by but we still need electricity. So let's talk about it in a slightly different way. So instead of electrocatalysis, means I supply using the energy is coming from electricity that I have to figure out some way of getting. How about we supply that energy from the sun? And then I don't care about the efficiency, you realize, because this is an infinite. Even if I get only 1% or 0.1% of that energy, it's still fantastic because it's free, correct? And there's no burden on it. So this is where, I'm sorry, it's in yellow, the word photocatalysis, but the idea is that we take inspiration from something called, I hope you've studied in school at some level, and it's called photosynthesis. And I'll give you how we're deriving it. I'm not trying to mimic photosynthesis, but I hope that I can explain to you what this is. What is photosynthesis? Photosynthesis is Something happens inside a leaf, and what you're doing is you're supplying CO2 and water, and what are you getting back? You're getting back food, which in this reaction we call glucose, correct? Let's just look at the reaction, all right? On one hand, just look at the carbon aspect. Isn't it lovely? You take a pollutant gas that we are polluting our environment with, and we are actually making glucose, which we can actually eat and use and so forth. Currently, as an aside, I'll digress again, synthetically, as chemists, as physicists, as biologists, we cannot do this in a beaker. We cannot mimic photosynthesis in a beaker. We see it happening all around us all the time. We are alive because of this reaction. That is the exclusive reaction, the reason we are alive. And it's a fantastic reaction because it's actually, now what is not written in this reaction is it an uphill reaction or is it a downhill reaction? Does it need energy or does it release energy? Think about it. I'm making a molecule that is glucose. Glucose actually stores energy. That is what we consume and we burn and we get our energy, right, when we eat food. So therefore, that's a energy containing molecule. Therefore, the reaction going from the left to the right is an uphill. It's an energy consuming reaction. And where is this energy coming from? It's coming from sunlight. It's not hooked up to any battery or electricity supply. So this is the inspiration that you can drive an uphill reaction using sunlight. So can we drive our same uphill reaction of water splitting with sunlight? Now you'll say, well, I have water, I have sunlight, but I don't see spontaneous breaking up of the water into oxygen and hydrogen. The reason, the crux lies in something called, which in the case of photosynthesis, the key is something called chlorophyll. You've heard about the molecule, but what you've not heard, and I won't discuss this, but I want you to realize the complexity of what's going on inside that leaf. It's a very, very complicated redox reaction. Again, there's a reduction and an oxidation, just like the water splitting reaction has, all right? But in this case, we are making, and I'll just move here. So here you're making the oxygen, and there's the Calvin cycle going from the CO2 to, so one is, that is basically the reduction, and this is your oxidation reaction going on, all right? It's the same thing that I tried to separate out in the normal 2-electrode system. So you understand about inspiration, taking an idea and saying, well, wait a minute, there's something very intriguing going on here. Can we try and replicate it, but not to make glucose? Photosynthesis is doing that for us, but I want to make hydrogen molecule. I want to take water and I want to split it. So again, I'm sorry. So this is that uphill reaction, kind of I said going up a mountain. But what I want you to realize is, so this is the up mountain, the water to the, this is the, there's something else that you need to realize. For a reaction, there's something called an activation energy. It's not only just going up the mountain, I actually have to traverse something called an activation. We can discuss why this is, all right? And this is the problem. Going from here to here, I can use sunlight, but overcoming this part, I can't use sunlight, all right? As you can see, I need more energy than actually would like. So what we do is, we use a catalyst. And what the catalyst does, just like the electrocatalyst, you can have a photocatalyst, and that decreases that activation energy. So you understand now why I still need more energy to drive my reaction. My net reaction is only giving me this energy, but I'm using a little bit more to get there, all right? But if I use the right kind of catalyst, I'm decreasing that burden, all right? And if I decrease this burden enough, in principle, I can use sunlight to drive this, all right? So in the presence of a catalyst. So I'm going to make a long story short. So what is a catalyst? Catalyst is nothing but some powder. As chemists, we make funny looking powders, structures, inorganic materials, all right, that are stable. They have funny stoichiometries, all right? And these are something called, the kinds that we work with are called semiconductors. And I'll try and quickly show you a little cartoon. So what happens is inside my catalyst, when sunlight hits, something goes from a ground state to an excited state. And I just want to show you that on the same thing, I have the oxidation and reduction going on. For those of you who want to know more, I will be happy to discuss it, but I don't want to. But on that particle itself, I have the oxidation and reduction. You understand, water is getting split and forming hydrogen and oxygen. So what is this telling me? That if I have this powder, this catalyst, suspended in water, I irradiate it with light. In principle, I should get oxygen bubbles and hydrogen bubbles. And there is the end of my talk. All right. So what I want you to see is, you see something pasted on a substrate. All right. There's a back and front of the substrate. The oxidation is happening one side, reduction is happening on the other side. You see the light being shown, sort of irradiated, and you see bubbles coming out. The efficiency is not fantastic. You can just see it from the amount of bubbles coming out. But those bubbles are hydrogen and oxygen gas. All you have to do is trap that, and we have not consumed anything. We just have water there, and we have sunlight shining on it.
How do you separate the two processes?
Okay, so that's not a complicated task. What you do is, in principle, you separate the two redox reactions. Quick way, easy school children way is you put inverted test tubes. The gas gets trapped, all right, inside, and then you can just pop it away.
So one
Hydrogen and oxygen separately.
Yes, 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 yes.
they're coming from different sides of the paper.
Yes, different sides. So one side is the oxidation, one side is the reduction going on. All right.
It's physical, basically.
Yes. So it's not, I'm not showing you loads of bubbles coming out, because this is not a trivial process. All right. This is lots of hard work gone into trying to make this solid material that will do this. I've really simplified many, 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 many things in here. But in principle, you can do this. All right. This material does not have any platinum in it. It's not an expensive material, but it does have a shelf life. It will not last forever, so you have to keep replenishing. It'll leach out, it'll change and destroy, and just like everything, every material in the world. And so you have to replenish it. But in principle, you can be generating hydrogen in a very clean way with absolutely no burden, and all this hydrogen is free to use. Therefore, you have not polluted and not dependent on any external source of energy, and you're just using sunlight to dry
You
this.
tried it with sunlight?
Huh? Yes, yes. So this, I should point out to you, this is not ours. I've given the name here. This person, his name is Daniel Nocera. He works at MIT. He is perhaps the only person who's made this. Okay. Yeah, so we can talk about all the other aspects about patents and privatizing and why oil companies buy your patent and then lock it away. They don't, because this would be a direct competition with them, right? And this will bring down the cost of your energy dramatically. Imagine if every farmer has access to their own hydrogen gas, then you have access to some form of energy. And it's a question of how you want to exploit it. You want to use it to form in a bus, or you want to combust it and create a electric grid out of it, or whatever.
And storage of hydrogen is not a
Okay.
problem.
So storage of hydrogen is a fantastic point. So it's a gas. So storage of gases, and this is a very combustible gas. You're going to see that. So the way people are envisioning, and currently the way it's getting stored, is think of it like a sponge in your mind. A sponge holds water. We can make sponges that can hold gas. And what you do is, when you will go to the petrol station, and how the fuel cells work is, so when you pump in the hydrogen gas, it sort of goes and adsorbs. You see, everything has a monolayer of water. I do not know if you realize this. Every surface around you, so water, which is in water vapor, gas state, actually adsorbs, and it's in sort of a stationary state, as it were. Okay? So same thing, hydrogen gas molecule can adsorb inside these porous sponges, where the pores are very, very small, because the hydrogen molecule is very small, and it adsorbs and it uptakes a certain large quantity, and you do it at a low temperature, slightly below room temperature. And then when you need it, means in the fuel cell, you elevate the temperature ever so slightly by 10 degrees, and the molecule gets energy and it desorbs from the material. So the storage entities are like a sponge, a gas sponge, but where the pores are very organized and very small. They have a certain chemical functionality, so they hang on to the hydrogen molecule. Does that, so yes, storage is not in a gas cylinder like you're conventionally familiar with. This is a much more refined way of storing it. And because you only want to remember, you only need a small amount to get a lot of energy. So it's not like you are, it's not like your CNG cylinder kind of thing at all. So something very different. Okay, so that brings me to the end of my talk. It's a little after. So we will do a few experiments if everyone's up for it, or you want to, or if you're interested. So we have the electrocatalysis set up. So I'll just show you quickly. It's very simple. So we have a beaker of water, right? I have 2 electrodes, which you can do at home. You can use pencils. This is graphite only, all right? 2 graphite stuck to alligator clips, the copper wire. And then we have and we have a 9-volt battery. I have the others. I have the smaller pencil cells, but I can tell you that it will not work. Suren, can you just help me? Sorry, this takes a few hands. So all you do is take your alligator clips and attach 1 electrode at one end. We can do this again for and the other end. Just make sure they don't touch each other.
Yeah, I will hold them.
Right? So now I just get close, and what I hope you
carry it around.
You can carry it around.
Yeah, just hold it apart.
Yeah.
Just can you hold it apart? Yeah.
I hope it's, yeah. So if you can just come around, you'll see bubbles forming at the 2 electrodes. So I hope you can see the bubbles coming out. Oh, that's good. Yeah. Oh, it's hold on.
वो पहले से इससे आवाज आ रहा था, कुछ प्रॉब्लम हो रहा था। I got it allowed to go talk to the
Is everybody okay, guys? I'm sorry. Can you see the 2 bubbles coming out, right? And you see lots of bubbles coming out because they're like nitrogens. You got it?
Yeah, here.
All right.
I can't see it because I have to follow.
Now, how do you know which one?
Yeah, whichever one's connected to which one. Basically, the hydrogen is the reduction reaction. It comes from a negative electron, the oscillation is the
Spark came from where?
Somewhere here.
Here.
Alright, so just like you can bubble any gas inside it, so we'll just have some hydrogen, and it's a mixture of hydrogen and oxygen. Remember, we need to combust, so you need oxygen in it. And then we're just going to burn it. You're going to get the popping noise. So the idea is that, at least for me, graphs and tables and numbers are very esoteric. You don't get the hands-on feeling as to the power of these molecules sometimes. You work with CNG at home, so you know how much when you burn your gas cylinder, and it's basically a fire hazard, and you know the amount of molecules. You do not use hydrogen gas for cooking. Now you'll get to see why you don't use hydrogen gas.
Bottle and just ignite it, and it goes and really creates.
Anyone?
That's the bubbles, yeah, not the water.
So, and we've not released any pollution, right? Sorry?
The reaction has turned back
Release the mix. If there are any questions, has invested quite a bit in nuclear energy. I do not consider it a green form of energy, but I do consider it a very valid form of energy. India is doing something which is interesting. You see, it needs uranium, a specific isotope of uranium, all right? And what we do, you basically break it up a little bit and instead of forming another entity, it forms a different kind of isotope. Uranium-235 goes to another isotope and energy is released. Now these isotopes are radioactive, so this is where people get very afraid. And you have nuclear other countries had invested, Germany, France, Japan. Japan has stopped doing it ever since they had a nuclear reactor where there was an accident. India is still investing very, very heavily because they're doing something that no other country is doing. Because what they're doing is they're using this, what they call spent fuel. So they go from one type of isotope, they go into another type of isotope. This isotope, the second one, they are reusing in the presence of polonium. Alright, so they use polonium and they make another sort of a nuclear reaction where they get more energy. Alright, and with this they do another one and then they get more energy. So they're doing what is called fast breeder, like a second generation and a third generation cycle. They're basically reusing in principle what was considered to be spent fuel, which was still radioactive, which needed to be buried underground. In America they do it, Europe they do it, and so forth. But India has found a way, has found a technology that they are not burying the spent fuel, they're reusing it into a second and third cycle. Yes.
Only India has this.
Currently, as far as I know, as far it's not, I would like to confirm that, but as far as I know, it's only the Indian scientists who are talking about it. It takes a lot of infrastructural investment into it. This is again not a small little thing. These nuclear power plants are huge entities, and yes, even after the 3 cycles, you are still left with radioactive waste. Let me make this perfectly clear. That's why I'd not put it under the green energy, but it's a fantastic. But this amount of radioactive waste is smaller. Am I kind? Yeah. Do you understand? So they are spending the amount. They will need to build a lot of nuclear. If you look at the calculation,
What are you using this nuclear energy for right now, India?
for electricity, electric supplies, they've attached it to the grid, but it's a very small amount. I'm sorry, I didn't show it in the pie chart because
It was there.
It's there, but it's not in the large quantity. Let me make, like I said, the biggest thing: wind farms, photovoltaic farms, nuclear energy. All right, all of these things need a large infrastructural investment that is different than a conventional coal power plant. Coal power plant people are familiar with. You just ship in coal and you burn it. You know, there's not a lot of fancy physics or science associated with it. So that is why, like I said, even up to 3-4 years ago, they were commissioning new plants, knowing full well the pollution hazards associated. Because at the end of the day, Modi needs to keep everybody happy, and you know, you guys will, we as a society will not be happy if we have power outages, right? What's the
Like now, see in Japan, there's a leakage,
right?
and they are such a more developed country than us, with more wealth, and they still battling that the consequences of the leakage.
Absolutely.
I mean, it's different leakage that will happen in our power plants. I don't know how we'd be able to cope with it. So it's
I'm just recording you.
manufacturing nuclear energy
Yeah.
is more of a risk. than
It
a help.
is a huge risk. So, what can I say? You tell me, is that radioactivity a huge risk, or the pollution that we are experiencing today a huge risk? Right? It's all relative. It's a perspective that you see. For a long time, people did not look at this pollution because you see, there's no science. We don't need to make gasoline. We just take crude oil and we do a little refining, which is very trivial science, and then we get gasoline.
Radioactive things go on from generation to generation to generation. It's sort of never ending. The harm that's done is never ending.
So you have to also realize the amount of the final radioactive material with respect to how much energy that it has generated during its life cycle. Now, I do not know these calculations, but for what it's worth, the scientists, at least in India, have done it, and that's why they found it much more lucrative, because we do have a large deposit of these radioactive minerals in our country. So they have found it as a country that it's still very attractive. Now I should point out to you, France is still continuing with their nuclear energy program. Germany has curtailed it, Japan has curtailed it. US is still continuing with it. Neither US nor France have these what are called fast breeder reactors, which we have. Now I do not know about the smaller countries. I'm sorry, this is just what I get to hear about in talks. So that is, I'm just telling you what it is. And they've invested, and they do need to. The amount of spent fuel at the end is radioactive, is hazardous. But if you take enough safety precautions, in principle, you can hide it away long enough that it doesn't harm anybody. And what they do is they bury it under so many kilometers under the earth. That's how they circumvent it. So there's no easy answer to every question. Science is trying, but you see. By the way, I should, we talk about the photosynthesis. I didn't highlight this, but you know how efficient photosynthesis is? We talk about efficiency and all of, by the way, nuclear fuel and gas, your engines are 99% efficient. The energy from your drop of your petroleum gives you quite a bit of energy, all right? Nuclear fuel efficiency is fantastic as well. It's in the 90s. How efficient is photosynthesis in terms of the energy that goes in and hits the plant and how much of it gets in? 0.04%. But it doesn't matter, right? Because it's free sunlight coming into the play. So that is where we have to figure a way out, but we have to find the right catalyst, work, and that can produce a lot of hydrogen, make it in a way that is conducive for fabrication.
Isn't it fantastic that we've never been able to replicate photosynthesis?
Absolutely. We can't replicate many things. We can't replicate. My favorite example is I work on this. Is our skeleton is made of bone. It's calcium carbonate. All right. Calcium. We make calcium carbonate. You know what we use it for? Chalk to write on the blackboard. That chalk is what makes your skeleton. Exactly the same chemical, and you are sturdy. That chalk is not. Because of the way nature makes it. So nature has a way of evolving over, has evolved itself. We derive inspiration. It's very difficult to mimic nature, but, that's the, yeah. We can't mimic photosynthesis, but then I'm not sure we want to mimic photosynthesis.
I have a slightly, really on a business and government side of things. There's this huge thing about how India's tried with this national solar mission and the motor vehicles policy, stuff like that. But at the same time, they've cobbled themselves with taxation and with industrial policy and with China taking over all the natural mines in, let's say, Central Africa. And at the same time, they're saying we will reach those targets by 2020 and 2030. Do you really think that science, when you said we're trying very hard to get there, do you think material science is up to the challenge of reaching those things?
It has to be. We have no other. We have to do it. The point is we have to move forward in life. And the thing is, otherwise, what is the result? I mean, what do? We can't just sit back on our hands and say, okay, let pollution override us. Let's take the easiest route out and let's deal with it.
What I'm going to ask is, considering you work in the field, do you think that technology is getting to that place where we can reach those goals?
I think we need lots of different kinds of technologies, and we are getting there. It's a question of implementing, and right now, one of the hurdles is money. As I hope I've shown you, we have green energy, we do not have cheap green energy. Now, question is, why is it so important to have cheap green energy? Why are we not just happy with green energy? And we are getting richer as a country, so let's pay some of that money from our pocket and buy more expensive energy that is clean. All right. So it's also about a mindset change. People want subsidies from the government. I think government can provide electric vehicles, for example, subsidies on electric vehicles that will decrease our burden on gasoline. But at the same time, we still have to provide that electricity for that electric vehicle. So, where does that electricity come from? The coal power plant? Or does it come from solar cells? If it comes from solar cells, there are other issues. Solar cells are made out of silicon. They have a lifespan of 20 years. You had talked about something being perennial. Nothing is perennial. Even solar cells, if you were to buy them, they have a lifespan of 20 years. You have to replace them. It needs silicon. India is making solar cells, but not from its raw materials. So it's just it's
Putting it together.
Putting it together. The assembly plant is in India, but not making it. It's the main crux of the good stuff still comes from China. So, it's not, I realize there are many problems, but I think even solving one aspect of these problems is better than not even tackling this. It's a cohesive approach. It has to be a combined approach, everybody from top to down, and whatever way you want to look at it. And I think, you see, my main thing is the government is, our country is very good at promising many things, and we get headlines, ye ho jayega, wo ho jayega. Things don't get implemented. And we are a rich country, believe it or not. I think we're a very, very rich country. It's a question of where we put that money. Now you know why in the newspapers you always have the coal mafia case stories about what's going on, and the people shipping trucks at night, because that's energy. That is the main commodity. It's not money. So, and I'll give you a completely side thing. So that Daniel Nocera's catalyst that I showed you, so I can tell you, so he basically patented and so forth, and then he wanted to create a company and manufacture and do large scale research so that he can make bulk of it and so forth. So Aramco, which is a Saudi Arabian oil company, got involved with them and provided lots of funding, and at some point something happened and they took all the patent rights and they put it under lock and key. They don't even give him access to it, right? Because they say, while we have oil, why should we pursue the renewable source? They're willing to, oil companies and other, business leaders, as it were, are willing to pursue renewable energies as long as it's still profiting. It should still be profit making. And until that happens, things won't. And how do we get around that? I don't know. But at least from a science point of view, we are trying. But yes, everything doesn't happen overnight. You can't make the cheapest, best, greenest material overnight. You have to try and understand the science, and it takes effort.
And then when you make the breakthrough, you don't give it to an oil company.
Well, by the way, there's an institute here in Matunga called ICT, Institute of Chemical Technology. So they are collaborating with ICT right now, and they're trying to make other kinds of biofuels, not hydrogen gas specifically, but you can make other kinds of biofuels. Methanol is a big one that people want to make, or they want to convert CO2. Right now there's so much, just like photosynthesis converts CO2 to glucose, why make glucose? Why not make CO2 to gasoline? Can we do that reaction? If we are going to spend gasoline, you might as well use the CO2 that we're making. So that's an uphill reaction, you understand? So they're working on those kinds of catalysts. So there are various directions people are taking.
Any further questions? This is a very exciting energy conversation with the lights going off, but thank you so very much.
Thank you for having me. I hope I was I was able to communicate some aspects. I didn't go too much into the science, but if anybody wants to discuss, I'll be happy.